Hello, thanks for attending this talk about Pulsar watermarking. My name is Aaron Wright. I'm a cloud developer at StreamNative, and we'll be talking through a proposal to improve stream processing with Pulsar topics using watermarks. This talk has two sections. First, we'll discuss, what is a watermark and what are some of the unique challenges faced in a Pulsar context. And then we'll look at a specific proposal to enhance Pulsar to deal with watermarks in a first-class way. Let's begin with the concept of a watermark. Simply put, a watermark is an assertion that all the events up to a certain timestamp have been observed. For example, let's say we have a stream consisting of events, each of which has an event timestamp. Ideally, we observe older events before newer ones. For example, an event at time 7, then 9, then time 10, and so on. In reality, streams are not totally ordered in this way. And when we're processing information in a stream, we'd like to be able to make some affordance for late records or for the disorder that might exist for many reasons, and we'll get into some of those a little later. A watermark serves as an assertion that all the events up to a certain timestamp has arrived. For example, when we look at this stream here, we see timestamps generally increasing and a watermark saying, well, at this point, you've seen everything up to time 11. What are watermarks used for is for stream processing. A modern stream processor takes information through a processing pipeline and performs various transformations or other operations on those events. Often those operations are time-based. For example, you might use a time-based windowing operation that aggregates information into time buckets. For example, you might want to create an hourly summary of some information. Given the unbounded nature of streams, how does one know when all of the information has arrived up to a particular point in time? For example, have we received all the records that relate to a particular time frame so that we can draw conclusions about that time frame? Stream processors use watermarks for that purpose. You might say that the watermark regulates the event time clock within a stream processor. This diagram tries to show that in action. For example, these yellow boxes depict how a watermark flows in line with events, and as these events and watermarks flow through a pipeline, each operator has a clock of its own, and the inputs that come to that operator determine, regulate or advance that clock. Because watermarks drive computation in a stream processor, the correctness of the watermark is very important to producing correct program output. Let's talk about how watermarks are generated. Usually watermarks are generated in a stream processor using a heuristic that depends on observation of events. It's intuitive that you expect the event timestamps to gradually increase. You process older information before newer information. And so a pretty typical heuristic is what's called bounded out of orderness, which means that if you observe an element with timestamp X, chances are you won't observe any future elements that are much older than X. For example, you might offer a grace period of 1 minute or something like that. That approach has a couple of big problems. Number one, it can introduce latency because of a very generous lag or grace period. Also, it's highly dependent on the order of observation. And though this, we often see diagrams that are idealized, in practice, the order of observation of events is pretty dynamic. We're going to look at that in the next slide. But let's just look at this picture for a minute. Here, for example, is a depiction of a bounded out of orderness generator. And in this case, it will use a lag or grace of 5 time units. For example, when we first observe an event with timestamp 7, we think, oh, well, I'm sure we've seen everything at least to timestamp 2. As we observe more events, that is still true. When we encounter 15, well, now we think, oh, well, we won't see anything older than 10. And guess what? Event 9 shows up and it has to be considered late. Why was it late? Was because a stream processor will have done its computations with this watermark in mind. This watermark told the processor everything up to timestamp 10 has arrived. So late events are a very unfortunate consequence of using a heuristic like this, in that it can produce inaccurate or chaotic results. For a stream processor that is processing events from a Pulsar topic, generating watermarks using a heuristic is pretty challenging. When you look at this diagram, the order of events received by a particular consumer is dependent on a lot of factors. Pulsar does offer a per key ordering guarantee, but doesn't strive to order information delivered to a consumer in event time order, whether across partitions or whatnot. And it can be, the ordering that you get is complicated by subscription modes, by the message acknowledgement aspect, by partitioning. Even transactions can have an effect on the order of observation of events. So what can we do about this? I'm here today to tell you about an idea called Pulsar Watermarks. This idea is captured in PIP 102. PIPs are the Pulsar Improvement Proposal process. What are Pulsar watermarks? A Pulsar watermark is a new type of message that's generated by producers, aggregated by brokers, and delivered via subscriptions to consumers. A Pulsar watermark is an assertion that's made by the producer about the progression of event time. Each producer makes their own assertions about the advancement of event time with respect to the events that they produced. The broker aggregates those assertions, those watermarks, so that the consumer may receive a more accurate watermark based on the acknowledged messages that they've received. Let's take a look at the proposed API. From a producer perspective, the API is extended to emit watermarks in line with messages. This means a new watermark builder is introduced into the API. A watermark consists of an event time. That's it. There's no payload beyond that. Also, the interface supports idling the producer. When you think about how the broker is aggregating watermarks, this aggregation occurs across all the producers that are contributing to the topic. We want this feature to work when there's numerous independent producers. And a producer is usually identified by name. So in the Producer API, when you create the producer, you have the option of naming your producer. If you don't provide a name, Pulsar generates one. These names are how we identify the producer's contribution to the watermarks. This feature is intended to work even across disconnects. So once a producer is contributing to the watermarks of a topic, that producer will be considered going forward unless and until that producer idles itself, which is a way of indicating that it should no longer be considered from that point on for the purposes of watermark aggregation. One other thing to point out is that transactions are fully supported here. So there's a variation here where you'll emit a watermark in the context of a transaction, and you can commit those transactions along with messages, as normal. Now let's take a look at the Consumer API. Consumers receive watermarks in band with messages. Now, depending on the language binding, there are different patterns to develop a consumer. One way is an event listener style called message listener, and this listener interface is extended to receive a watermark as it arrives. Those watermarks will be received on the same thread as messages. An alternative is the pull model, where typically an application calls receive, which is synchronous and blocks until a message arrives, or asynchronous, in which case you get a future. To support this pull model, at any time the consumer may query as to what is the latest watermark that has been dispatched to this consumer. Our goal is to support all subscription modes. This is, one of the great things about Pulsar is there's different strategies that a group of consumers can use to work together to ingest a topic. For example, there is a failover mode where one consumer will process all messages unless the consumer fails, in which case the system will fail over to an alternate consumer. A more popular mode that was introduced recently is the key shared subscription. That's where the topic is delivered to consumers such that any one key is guaranteed to go to the same consumer. This lets consumers, divvy up the key space and ingest it. When you think about how watermarks should work in these different modes, one, it's important that watermarks track the acknowledged messages. In other words, if some messages are delivered to a consumer but aren't acknowledged, it would be premature to hand out a watermark to other consumers based on that. The system must wait for the messages to be acknowledged before we can conclude that the watermark should advance. And when the watermark does advance, it advances for all consumers. Similarly, with key shared, when you think about it, each consumer is observing a subset of the topic. And a watermark generator that is based on a heuristic would have the problem that it is being driven on incomplete information. So one of the great things about this feature is that regardless of the subscription mode, the broker takes care of figuring out the advancement of the watermark such that consumers get correct results. Let's discuss how the Pulsar broker brokers watermarks. This diagram seeks to show the evolution of the watermark within the broker. And the broker is materializing a watermark. And this diagram can be thought of as like a dynamic table. Let me describe how to read it. Imagine we have a ledger and a cursor that is advancing through this ledger from right to left. It encounters message from producer A with timestamp 1, from producer B with timestamp 2, and then it encounters a watermark from producer B. Producer B has indicated that all events up to timestamp 2 have been produced. But producer B doesn't know anything about producer A and isn't responsible for making assertions on producer A's behalf. It's the broker's job to aggregate those assertions. And so we take all this information up to this point, and we see producer B has given us a watermark of 2. Producer A hasn't given us any watermark yet. And so the minimum across those is 0. Let's continue. Now we continue to read a little bit longer, and we reach a watermark from producer A. Here you see it's timestamp 3. And when we process that, now our table shows that producer A has given us a watermark of 3 and producer B of 2. Therefore, the global minimum watermark for this topic as of this point is 2, and that can be dispatched to any consumer associated with this subscription. Now let's take a look at how this would work in a stream processing application, say based on Apache Flink. In fact, there is a really great Pulsar connector for Flink that lets you use Pulsar topics both as a source of information and as a sink. This connector is called the Flink Pulsar source and exists today. Flink has a programming model for generating watermarks. It includes, heuristic-based generators like we talked about earlier, and those work by, observing events that are produced by a source. It is also possible for the source itself to produce watermarks. In Flink, this is called a source-based watermark strategy. Our proposal is to introduce a Pulsar-specific watermark strategy that draws watermarks directly from the consumer API, as we saw earlier. In addition, the Flink Pulsar sync has been enhanced to emit watermarks that arrive from the Flink pipeline. This allows you to construct multi-stage pipelines where the time information that comes from a topic flows through a Flink pipeline, goes out to a topic, and so on, can flow across these stages with high fidelity. You no longer need to use a heuristic at each stage to, reconstruct the time information. Now Pulsar will be able to actually store this information and replay it in a downstream pipeline. Let's recap what we've talked about. PIP 102 introduces an enhancement that will propagate watermarks from producer to consumer. The rationale is to improve the correctness of stream processing applications that use Pulsar topics. Also to encapsulate the system internals of Pulsar so that the behavior of stream processing applications is more consistent and works for multi-stage pipelines, for event-driven microservices, as well as working better in unified stream processing scenarios. Let me give you an update on the status of this project. PIP 102 is the proposal and is in discussion. Please feel free to participate on the dev channel and also take a look at the PIP itself, which is linked here. This was prototyped earlier in the year in the 2021 Apache Pulsar Hackathon. Take a look at this link. You can see a prototype implementation, demo applications, and more. So with that, I want to thank you for attending this session, and I'll see you online.